Many of you guys asked me if I could do a system design video about how to design Twitter. And that's exactly what we're going to do today. Let's get into it. Now, as with many of those system design interview videos, this is a very, very broad question. And if you get asked this question in an interview situation, remember to stop there and not run into one direction and clarify the problem statement. So what we could do in this case with something like designing Twitter is talking about a couple of features, showing the interviewer that you have a good picture about the service and you can talk about different topics comfortably. And then identify maybe 2 or 3 core features which your design will cover. So in other words, nobody expects from you to design the whole service with all of its features in a 50-minute interview on the whiteboard. So you take 2 or 3 core features and you get into more details there. And remember, every time you notice that the interviewer wants to push you into a direction, it's because he is tasked to find out 1 or 2 properties about you. So let him or her guide you in the direction the interview is going. Now let's start with Twitter itself. You could think about a couple of features with Twitter, but what are the most important ones? Certainly tweeting itself, so sending a tweet, and then having a timeline, similar to Facebook or other social medias, where you see other people's tweets and you see your own tweets, and you see maybe tweets where you don't follow that person directly, but somebody else of your of people you follow reacted somehow on that tweet. So one of the core features could be just tweeting itself. So the second feature will be something like having a timeline. And in the case of Twitter, a timeline can mean 2 things actually. Because if you think about your own timeline, where if you are on your profile, you see your own tweets and tweets you retweeted, right? So whatever happens with those, you see on your own timeline. And this is what Twitter calls the user timeline. And then the timeline you see where, if you just go to twitter.com, you land on your so-called home timeline, which this is the timeline where you see all the tweets from people you follow. Now, with the user timeline, that's definitely the easier one to design, because all we do is take your own tweets and take your own actions, so to say, and list them up. Okay? So for this video, let's concentrate on the home timeline, where we, so to say, have all the tweets from people you follow and we merge them in chronological fashion. And the third core feature we need to take care of with Twitter is following, right? So following means you have your profile and you click follow on someone else's profile and you want to see that someone else's tweets in your home timeline. Now let's talk about a naive solution first, because we're going to talk about a little bit more about the better solution for a bigger Twitter version. But a very naive solution for a social network like Twitter could be using relational databases like MySQL, where you have a user table and a tweet table. And that means the user tweets a message, and that's just one record in this tweet table. So let's see. Okay, so that's the user table, that's the tweets table, where the tweets table contains more or less all the tweets globally. And the tweets table has a column which is called user. So this is going to be the primary key of this user table. User points to the primary key of the user table, meaning this one user tweeted this tweet, where, as I said, this table, the tweets table, contains all the tweets globally. So this would be a one-to-many relationship, where one user can have n amount of tweets. Now, if you think about this, what would happen if the user accesses his home timeline? It would mean that we need to know who this user is following, and then do a big select statement over this tweets table and do a select of some sort, like give me all the tweets from all the people I follow and merge them in chronological order, right? So every time we access the Twitter website, we would need to do this huge select statement and scan this whole huge tweet table. So thinking about this, you already see that this is, at some point, this is impossible to do because the tweet table will get huge. Of course, you could do things like sharding the database, maybe having newer tweets indexed, stuff like that. But happily, we know what Twitter does, or at least did 2 to 3 years ago, because there is a really good talk by the VP of engineering at Twitter. So I can tell you what Twitter did to solve this problem, because what they have are multiple thousand requests a second for displaying the home timeline. So doing this big select statement between those two tables, and then also having a third table involved where the table contains maybe all the people this user is following. So when we think about a better solution for this, let's think about characteristics of this system. Twitter, as many of those newer social networks, is very read heavy. That means lots of people access Twitter and read a lot, but they certainly do tweet as well, but not as much as reading it. So what we need is to have a super fast read function where you can access your home timeline in less than a second, possibly. And what we also know about Twitter is that, similar to Facebook and other networks, we do care about speed from a consistency perspective, so that if you tweet or if you post on Facebook, somebody else has to see that post as fast as possible. But we care more about availability. So that means it's not too bad if somebody sees your tweet 30 seconds after somebody else, but it would be really bad if one of those two people can't access your network. So we care more about availability and a little bit less about consistency in a extremely tight time frame. So this is called, and you will hear this a lot, this is called eventual consistency. Now let's get rid of this solution and see how we can do it better. Okay, let's start from the very beginning, from the user perspective. You are the user and you want to tweet something. So think about the website and the browser where you will have your tweet, right? This is the send button, and this is the content of your tweet. So you hit that send button and your tweet will hit some kind of gateway which Twitter has in place, because this is probably just a simple put or post HTTP call, right? So let's have a put here, and what you will always encounter with big systems and also smaller systems, to be honest, is a load balancer at this point, because Twitter has multiple data centers in multiple regions and maybe caching in place and whatever it may be. So you need some central point close to your region possibly, where your API call lands and then gets distributed to a machine or a data center which has capacity to serve you, right? So this is a load balancer, and this distributes your action to a machine. Now, after hitting the load balancer, Twitter does something they call fan out. So fanning out, it means they take your tweet and they put it in a in-memory database. That means what they do is pre-computing all the home timelines of everybody you follow. Okay? So this sounds crazy in the first moment because it means they pre-compute something and they store something in memory where we don't even know if that person that is following you accesses Twitter in the next few minutes. Maybe he doesn't look at Twitter in the next few days. And still, his home timeline is getting refreshed and recomputed every time somebody updates or posts a tweet this person follows. So this will look like this. The load balancer pushes your message into a Redis cluster. So Redis is one of those pretty famous and pretty well-known in-memory databases. They're more than in-memory databases in reality, but they're mostly used as in-memory databases. So what Twitter has here is a Redis cluster. And because I mentioned that availability is so important for Twitter, they not only store the home timeline of all those users in one Redis database, every home timeline is replicated 3 times. So you sent that tweet and it lands in 3 Redis machines in memory. In memory meaning that they're not stored on a spinning disk, they're stored in RAM, right? So something you could mention here to the interviewer is those Redis machines need to have a huge amount of memory and RAM to store all those tweets. One way to optimize this would be to store those home timelines only for users which were active in the last few days or weeks. So if you notice that a user profile which normally would get that update here is not active for 2 weeks or something, then he will not, his timeline will not get updated. And that will also mean that if he revisits Twitter some point in the future, his first visit there will take a little bit longer because then they need to recompute his home timeline at that moment. It's not pre-computed for him. So let's take a look at what exactly is in this Redis cluster. Mainly, these are lists, native Redis lists. And as I said, every user has one list per Redis machine, so to say. So your home timeline per user is in here. So let's say this is user Bob. And this is his list in Redis, right? And it will be on every of those 3 Redis machines. So this should look identical on all those 3 machines. And of course it can happen that one of those machines was available at that point and will get updated faster than maybe the second one, but eventually all of them will show the same state. So user Bob has this list here, and it contains something like a list of tweets which represents his home timeline. And that means it has a tweet ID, and it also means we need to know from where this tweet come from. So we could store all the information about the tweet itself in a different table, but maybe it makes sense to have not only the tweet ID but also the sender in there, right? So this is user Bob's list in Redis, and up here, this person is maybe Alice, right? And Bob follows Alice. So Alice triggers this thing, and let's say Alice has 100 followers. That means that when Alice sends a new tweet, 100 times 3, so 300 Redis lists will get updated, given that all those 100 followers are active Twitter users and are not in some sort of hibernation state. So Alice does it, this gets done for Bob, so her tweet lands in here, and this happens 300 times because Alice has 100 followers and the update is getting replicated on 3 independent Redis machines. Now if we do this, the interviewer could ask you what is a problem, what could be a performance problem with this architecture. And as we saw, Alice has 100 followers and those actions are done 300 times. So what if somebody like Lady Gaga or Justin Bieber tweets something? That means all of their followers, millions, 30, 40, 50, 60 million Redis lists will get updated with one tweet, right? This is a huge computational load for Twitter, and they did this solution, they're still doing this solution as far as I know, but they needed to find solutions where they could circumvent this. Because what happened is, it took very long for all of those user lists, all of those Redis lists to update. That means that if some of those celebrities tweet, there were people seeing that tweet and reacting on that tweet, while other people didn't see the original tweet of, let's say, Justin Bieber, but they saw the reaction of their friends, because their reaction, the friend who you're following has only 100 or 200 followers, so his replication is a lot faster than the one of Justin Bieber. So they had to take care of those edge cases where people would react on a tweet and you wouldn't see the original tweet people reacted to, but you saw their answer. So to solve this problem with a couple of users who have millions of followers, you could incorporate the SQL approach. So let's say Alice and Bob both follow Justin Bieber and a couple of other people. But if Justin Bieber tweets, this is not happening when, for example, Bob accesses his timeline. His timeline will get pre-computed with everybody else except Justin Bieber, and then Justin Bieber's tweets will get merged during load time. Because then when Bob accesses his timeline, everything is pre-computed, just a couple of tweets from very famous people will get inserted at runtime, so to say. Okay, now this is somehow covering all of those 3 core features. What we need to add here is the feature of following. So in here, there has to be a point where after the load balancer hits this and then we populate those Redis lists, we need to have a place, a database table where we know who is following Alice. So those 100 followers, we need to know which lists have to be updated there. So this is a step in between where this maybe doesn't have to be in an in-memory database, because we're doing this fan out as a process which takes some time, because we don't expect Bob to refresh his timeline in that moment. So this could be a table which only contains followers for Alice. So pudding goes to the load balancer. After the load balancer, there will be a machine or a step where we check for the followers, and that followers table will give us all the Redis list IDs here, which we have to pre-compute. Now, what's also interesting is to talk about the trade-offs of this architecture. Why is this the idea? Why are we proposing this? We talked about characteristics of read heaviness, so we need to have fast reads. And we also talked about eventual consistency. And we also talked about, we didn't talk about, but we should talk about space. So because Twitter has a limitation of 140 characters, and we're mainly dealing with characters, not with video, for example, space is not that big of a problem. So this is definitely taking a lot of space because we're replicating every home timeline 3 times. But because those tweets are mainly characters, we're fine with that. We are sacrificing a lot of memory to have very fast read times and very fast performance when somebody accesses his home timeline. Now, to finish this up, we'll take a look at what happens when Bob accesses his timeline. Okay, so Bob starts in the browser. And the browser again hits a load balancer first. The load balancer will point to a machine with capacity to serve this GET request. So this could be a big GET request here, because we want to see the home timeline of Bob. And now again we're hitting our Redis cluster, where only one of them has to answer, right? Because we know 3 Redis machines will have Bob's timeline in memory. So the load balancer can reach out to 3 of them where it knows that Bob's timeline is stored. And the fastest one that responds will get redirected to Bob. So the answer, which is the fastest from Redis, is the one that Bob then sees. So fastest one, let's say it's the second one here, will then populate Bob's timeline. And it's a pretty comfortable, pretty nice solution, because we're doing a lot of computation when somebody is tweeting, but as soon as Bob enters his browser and accesses Twitter, he'll get a super fast response. So one more detail for this access diagram. At some point, the load balancer or a machine in between has to know which Redis machines to query, right? Because potentially we have hundreds and thousands of Redis machines where only 3 of them have Bob's home timeline stored. But this can be done with a really fast hash lookup, because we know Bob's user ID and Bob's identity. So in between there will be hash lookup, and that hash lookup will tell us the IP addresses and identities of 3 Redis machines which have Bob's home timeline stored. Now, a couple of interesting follow-up topics for this interview question. We treated tweeting, timelines, and following, but what you could also talk about is search. And in reality, this talk I mentioned in the beginning, and I will link to it in the description of this video, the search pipeline when a tweet gets sent to Twitter is totally independent from this home timeline stuff. So with search, as soon as Alice puts her tweet into this load balancer, it triggers the fan out, what they call it, but it also triggers a second totally independent architecture which stores this tweet and indexes this tweet, so that when you in the search bar in the top, search for a tweet, you can find that tweet as fast as possible. So you could talk about searching, you could talk about notifications, push notifications. Twitter was huge on text notifications, on SMS notifications in the past. So they have lots of people tweeting and lots of updates on tweets. So the volume of push notifications has to be huge as well. And what you can also talk about is how to incorporate advertisement, because they know, so all those social networks, they know a lot about their customers, they know about preferences of their customers, they know about products they're interested in, and you could talk about how you can ingest all those analytics data and place effective advertisement tweets in a timeline, for example, similar to what Twitter or Instagram or Facebook do at the moment. Okay, this is today's video. Please follow us on Twitter now that we talked so much about Twitter in this video. The link is in the description below. If you have any questions about this architecture or any wishes for other system design videos, leave them in the comment section below. My name is Ramon Lopez and this is Success in Tech.